It's like how I grade, you know? Two sick boys is that. Okay, so for kinetics, again, if you did not get the multiple choice questions, they are right here. The answers are online. If you ever need the answers to these multiple choice or free response questions, and for some reason you can't access them online, if you want to, whether it's like during class or during a study hall, take pictures of the book that they come out of, you can do that too. But they are all online. Everything except for Big Idea number 5, which is what we do Monday, like every big idea. So 1 through 4 and 6, along with some stuff about the lab, that's all already posted online. So what we're going to do now is we're going to just go through some kinetics. We talked about factors that affect reaction rate today in class. Some people or some classes we got more in detail than others because of the schedule this morning. But so some factors that affect reaction rate, the state of the reactants. So whether you have solid, liquid, or gas, or whether you have more exposure. Right? Think about, when you're thinking about reaction rate, you want to think about movement of molecules and how many collisions they have. So if you're thinking about like states of matter, which states of matter would have the faster reaction rates? Yeah. Gases, right? Because gases move the fastest, so since they move the fastest, they collide more, and they have faster reaction rates. Solids don't react as quickly as gases do. And then again, surface area, when you think of surface area, think of exposure. I know you guys are used to like actually calculating surface area, but think about exposure. The more it's exposed, so a lot of small crystals have much more exposure than one big sugar cube or a cube of anything. And then temperature, again, think of movement. What's the definition of temperature? Average kinetic energy. Don't forget that. Right? The definition of temperature is average kinetic energy. Unless you change the temperature, you're not changing the kinetic energy. But the more kinetic energy that you have, the more collisions that you have. Concentration, again, of reactants. We are only concerned with reactants in kinetics because when you write a rate law, it's rate equals K times the concentration or times the pressure of reactants, not products. And then catalyst. Make sure when you're talking about why a catalyst works, talk about lowering activation energy. Don't just say, oh, a catalyst speeds up a reaction. Well, yeah, but tell us why. Right? Because it lowers the activation energy. Remember that the collision theory says that there are two things that have to happen for a reaction to occur. They have to collide with correct orientation. That's always what people forget. Correct orientation and then correct energy. And that correct energy being activation energy. So determining rate order. Talked about this a little in class as well today. Rate law has the form rate equals K times the concentration of A times B times however many reactants there are. Products are not included in the rate law. And then your exponents are from the data, not from coefficients. So you look at a table like this. This is what was it, third period when I couldn't do math. This is more of like the data table that you would see. Math is already done for me. So you're looking at concentration. So when you're looking at A, concentration of A is doubled. Okay, what do we want to make sure is true of B when we're comparing A? Stays constant, right? It needs to be the same. So when this doubles, this stays the same. So what does that mean about A? It's 0, right? When this doubles and this stays the same, it's 0 order. A has no effect on the rate. If you look at B, keep A constant. When B doubles, the rate doubles. That's first order, right? And so if we wanted to write the overall rate law, or the rate expression, it's just rate equals K times the concentration of B. We don't include A because it's 0 order. And then we could find the rate constant. We could just plug in some numbers, use the data, and use the rate law to find K. And then you have these three graphs. Okay, we talked about these today. 0 order is when concentration versus time is a straight line. Always look for the straight line. ln versus time, if that's a straight line, it's first order, 1 over, and time, if that's a straight line, it's second order. You can find the integrated rate laws on your equation sheet. Right, the integrated rate law, the first order one is the ln concentration of A, second order one is the 1 over concentration of A. Okay, and then with half-life, the only half-life you need to know is first order, because you're given that half-life equation on your equation sheet. On your equation sheet it says T1 half equals 0.693 over K. That's just the actual numeric value of ln2. So that is first order. Some things with half-life. Talked about this as you did the free response questions today. If you didn't get the free response questions, you can grab them from me tomorrow. I know, like first period, some people got them, some people didn't. But one of the free response questions dealt with half-life. And so remember, the half-life is just the time that it takes for the concentration to cut in half. Some half-life questions are going to be much easier than others. The half-life remains constant in a first-order reaction. So if it's a first-order reaction, the half-life is going to be the same no matter what. Second-order reaction, half-life actually changes as the reactants change. But if it's first-order, your half-life stays constant. So if you have a first-order reaction and your half-life is 10 minutes, your half-life is going to be 10 minutes whether you have 100 grams of something or whether you have 0.1 grams. Your half-life will still be the same. And so then here's an example, and notice it has some particle diagrams. So in this example, when the half-life is 30 seconds, okay, the concentration gets halved every 30 seconds. Okay, so we have initial. Okay, molecules and moles we can use interchangeably with particle diagrams. So we have 12 molecules in the box. Notice the box doesn't change. Keep volume the same. So we go from 12, and then after 30 seconds we go to 6, and then after another 30 seconds we go down to 3, and then after another 30 seconds we have 1.5, all the way down. You never hit 0, right? It's going to be exponential, so you're going to be really, really close. Like you'll be down to a number that's like 1 times 10 to the negative 100 and something, but you never hit 0. That's the whole idea of the exponential, the half-life. Okay. Then we go to reaction mechanisms. So mechanisms are when we have multiple steps, and cross your fingers that slow step is first. So we have a reaction, and it's experimentally determined rate law, right? We can't change, or we can't use the stoichiometry to determine the rate law. We have to use data. So a chemist proposes 2 different possible mechanisms for the reaction, which are given below. So we have mechanism 1, we have mechanism 2. And notice the slow step is the first step, which means, how do we find the rate law in a mechanism? Use the slow step, right? It's going to be the same as the slow step. So what we need to do is we look at this and we see, okay, rate equals K times concentration of X2. But now the difference is this is 3 steps, this is 4 steps. This is based on the information above, which of the mechanisms is or are consistent with the rate law, and then list the intermediates. So first, talk about intermediates. What is an intermediate? Talked about it a little bit today. Created and then gets used up. So what we want to do is we want to find whatever gets created and then whatever gets used right back up. So if we take a look at mechanism 1, what's an intermediate? Okay, the X's. Anything else? So we said the X's are intermediates. What else gets created and then used right up? X, Y, 2. Okay, so there we have those. And then in mechanism 2, we have the X's. What else do we have? Okay, XY gets made and used up. Y gets made and used up. And X2Y gets made and used up. Almost think about it like Hess's law. Right? Whatever you can cancel is usually an intermediate unless you start with it and end with it. Then what's that? Catalyst. Okay, so Based on this information, talk to the person next to you on which one of these is going to be consistent with the rate law and maybe why. Okay, so both actually are consistent. Okay, because how do you write the rate law?
It's just the slow step.
It's the slow step. And in both of the mechanisms, what's your slow step? Yeah, x2 going to 2x. Okay, so both are consistent. Now you could go through and try to analyze it even more and figure out which one might be best, but that's not asking you which one is best, it's just saying which are consistent. And so both are consistent because the slow step is your rate determining step, and that's what you use to write your rate law. Okay, so then here's a multiple choice question. The rate law for a reaction is found to be rate equals K times concentration of A squared times the concentration of B. What is the intermediate and which of the following mechanisms gives this rate law? So as you're going through, see if there's any that you can eliminate. I'll give you a hint. There is only one of the mechanisms that works. Well, how do you write a rate law? You're doing a mechanism. Okay. A squared is your rate law plus B squared. It's not just A squared. Yeah. It is, but step 3, you just use the slow step, right? So your answer for this one is actually mechanism 2. Okay? Remember, to write the rate law, you use the slow step every time. If you were to write the rate law for mechanism 3, what would the rate law be? Yeah, it's going to be rate equals K times the concentration of A squared. Well, we need A squared times B, so mechanism 3 will not work. So we're going to look between 1 and 2. Always write the rate determining, or the rate law by the slow step, by the rate determining step. If you write the rate law for this, it would be rate equals K times what? E times B. And what about down here? E times A. Right, but we can't have E in the rate law because it's an intermediate. So this is when we have to go back in and we have to do some algebra. Okay? When we go back in and we have to do some algebra, we need to remove this. So that's when we set these equal to each other. So we'd have A times B equals concentration of E. Up here we'd have A times B equals concentration of E, and then you plug concentration of E in for the slow step rate law. If we plug this in, A times B would give us what? AB squared. We don't want AB squared, we want A squared B. So if we plug A times B in for E here, you get A squared times B. Okay? And so we have to essentially replace. We replace, you use, what's that? Not system of equation, substitution. My math is all over the place today. We have to use substitution. So right here we take E equals K times A times B. Plug E in for E, you get A times B times A equals rate. Okay, then we have these reaction mechanisms with the graph, right? Energy profile or reaction diagram. This is to draw and label the axes for the energy profiles below. Match the curves with the appropriate description. Okay, so you have 6 possible curves, okay, and then you have 6 descriptions. So really what I want you guys to focus on is trying to match the description to the diagram. Now, let's kind of think about what this means again. What is usually on your y-axis of these reaction diagrams? Energy. So it's energy, and usually it's just, they usually say reaction pathway. So it's as the reaction proceeds. You always start with what? Reactants, right? And then we end with products. So talk to your group about this.
Like really into it. Okay? Just let me be into it. Like last year, the way they were saying, I can go back to sleep. Never done that? That's so fun.
Reminds me of something.
So I would just walk in, and like, hey, I will walk in a blanket and a little and I'd be wearing like evil clothes. What's the blanket for?
Oh, okay, so it's like
It was part of the play. I don't know. And then that's where the play's about. It was weird. I was in one time and then I just
Okay, let's take a look. For A, exothermic reaction with a two-step mechanism where the first step is slow. What does it mean if the first step would be slow? High activation energy. So, A is going to be this one. Okay, it's exothermic because your products have lower energy. Lower energy means that your reactants need to release energy. Slow step is the one that's going to have the highest activation energy. The highest activation energy is going to be the slow step because it's a bigger barrier to get over. Okay, and it's two steps because it has two humps. Okay, and then B, an endothermic reaction with a two-step mechanism where the second step is slow. What would you guys guess for that one? Okay, bottom middle. Endothermic means your products have to have more energy. You have to put energy in. And then again, the slowest step is going to be the one with the highest activation energy. Okay, so then for C, exothermic reaction with a two-step mechanism where the second step is slow, that's going to be the top center. Okay, and then, endothermic reaction with a two-step mechanism where the first is slow is going to be the very first one. And then E, exothermic reaction with a one-step mechanism. So which of the ones that is left is exothermic? Top or bottom? Okay, bottom, and then that leaves us with the poor endothermic reaction left. Okay, so this is looking at the reaction mechanism and the energy diagram. Okay, and then last but not least, we look at catalysts. Okay, so the whole point of a catalyst, I think this is actually the exact diagram I showed you today in class. The whole point of a catalyst is to lower the activation energy. That is why a catalyst works like it does. It lowers the activation energy, makes it easier for the reactants to get to the transition state to become products. A catalyst will help by allowing a new intermediate to form. Okay, but a catalyst is not used up. Okay, a catalyst is not a reactant, nor is it a product. It's just there. Okay, and then one example is in the Haber process. That's how they make ammonia, which is what smells. It's in like Windex, also in cat pee, but you know. So it smells really bad, and they use a catalyst in order to make it easier, provide a lower activation energy. And then this just shows the particle diagram, because again, they love their particle diagrams. And so what it does is it simply lowers the activation energy that's needed in order to create your products. Okay, and so catalysts, like I said, they provide a separate mechanism with a lower activation energy. If you have acid-base, you can have a catalyst that actually will gain or lose the proton, and that's going to make the reaction occur faster. So if your catalyst actually helps to take part in the reaction, it's not used up, but it just helps the reaction occur more quickly. Surface catalysis is when you put it on like a metal surface, or sometimes what they'll do is you'll have some sort of metal catalyst, like titanium maybe, platinum, and they'll actually run gas right over top of it, and that actually helps to speed up the reaction. That actually provides a lower activation energy. Or very common example in biological aspects are enzymes. enzymes help give proper orientation for reactions to occur. And then again, with catalyst, if you look at the reaction diagram, just lowers your activation energy. Oh, that's it. Ta-da! Look at that. It's 3 o'clock. Done. Yeah.
Yeah, it goes 3 to 6.
I'll go back. This is what I probably did. I'm not talking about how there's no, here, I'll put it on right now. Guys, if you need the questions, they're right here. Monday, we don't have this tomorrow, don't forget. No Fridays. But Monday is thermo count, and then Tuesday is equilibrium.
Kind of glad I want to see no, I don't want
Because all it's showing in that little dip, that's actually your transition state. So instead of your transition state flow, it actually just makes it easier for your transition state to form. The two-step doesn't actually turn into a two-step. All it does is it lowers the energy of your transition state. Because as soon as it hits that transition state, it's so unstable. What are we on? You are
Miss Carney, quick question for you.